Hello, everyone, and welcome to the next in our series of HECSTAB and HECSEL webinars we're providing. For this webinar, we're going to be discussing wind modeling and analysis in HECSTAB and are showing off our new software package, Herbert-ABS Wind. Brandon Wee is a new developer here, and he spent a lot of time working on this, and he'll be presenting this webinar and going through the various modeling aspects of the program and then the calculation aspects as well. So without further ado, I'll turn it over to Brandon and let you take it from here.
Hello, everyone. As Mike said, I'm Brandon Wee, and today I wanted to talk about sort of our new developments that we've been working towards. And as Mike said, wind modeling and analysis, both in HECSTAB and the new tool Herbert-ABS Wind. To give a brief high-level agenda of what we're going to be going over today, we're going to start with sort of wind modeling and definition of sort of the wind calculation in Ship Project Editor. And next, we're going to move into doing an overview of the new Herbert-ABS wind analysis tool. We'll look at some of the important wind calculation settings that are exposed in that tool and do a quick run through on a sample semi-submersible vessel. And then finally, we're going to use the results from our wind analysis tool to run a wind analysis in HECSTAB with the same ship, doing, in this case, a intact max kg analysis. So looking at Ship Project Editor, we have three main wind definitions available for ships and offshore structures. The first one here being the wind profile, which is sort of the simplified and most simple wind definition we have available. Basically, we're looking at the vessel transversely and grabbing the exposed profile of the vessel in all the hull compartments that are defined in the vessel spaces. And so this wind definition is typically limited only to evaluation for beam winds. And so it's typically only used for ship shapes where our primary heeling axis is the longitudinal axis. Here on the right, you can see we have a snippet from Ship Project Editor for our sample tanker model. And you can see it basically just takes the profile outline in this yellow, and the area exposed is the green hatches here. And this can be generated automatically from just the profile view of the vessel, or we can go in and manually edit the outline to make it more complex or simplified as we need for analysis. Moving on to a more complex wind definition, the second one we have available is the idea of a wind table, which is essentially a matrix entry of wind overturning moments for different wind directions, inclinations or heel angles, vessel drafts, and trims. And so this is a very involved process where we go in, and for each different combination of these values, we have to enter in the wind overturning moment. And so looking directly into Ship Project Editor, you can see here we have the vessel we'll be looking at, the semi-submersible, which we'll talk in more detail later. But we can go into looking at the wind table, and first thing we're presented with are these wind type settings. And so we can have different wind types and primarily differing by the wind speed. So we can have different tables available for normal operating conditions with maybe a lower wind speed versus something like a severe storm or survival situation with a much higher wind speed to evaluate. We have options on our entry, either using overturning moments or using the upright drafts, and also the different interpolation types that we'll look at between any of these different entries in the matrix table. And then finally here we have the not yet filled in moment entry. And so you see here we have all the wind directions going down along the column, and then we would enter in the overturning moment for any of the different drafts, heels, or trims that we would have entered. And so this process can take quite a bit of time to go in and enter all the values, especially if you have multiple inclinations and trims. And so recently we've developed with a client a macro to be able to speed up the entry of these from an existing text file. And so what I'll do is I'll go in here and open up the macro, and you can see we're going through and looking at different wind speeds, drafts, trims, heels, and headings. And I'll start by opening up the expected text file for what we're going to be bringing into Ship Project Editor. And so looking through, we have how many wind types, or essentially speeds, that we're looking at. We have the different number of drafts. So we'll have 2 drafts for this entry, 3 trims, 13 different headings, and 7 heel angles. And then up top, we define each of those values. So the wind speed will have 1 speed at 51.44 meters per second, our different drafts, trims, as I said, headings, and heel angles. And then on each line, we have the index for the wind type that we're looking at, the draft, trim, heading, and then going across, we have the different wind overturning moments separated by commas for each of our different headings. And so what I'll do is I'll go ahead and I'll run this macro with our moments text file that we just showed, and then come back into Ship Project Editor, do with a little refresh, and you can see now we have the headings that we defined from that text file, all the different inclinations, trims, and drafts. And for each of any of these combinations, we have the overturning moments from that file. And so it's a nice little way to sort of speed up the entry of this if you already have your wind analysis results from separate analysis program, and can easily be edited in a CSV file in Excel to be brought into here rather than entering each of these manually. And so the advantages of this sort of wind definition approach is that we can take wind heel or wind heading angle into account. So it's much more suitable for offshore vessels where the primary longitudinal axis is not necessarily the heeling axis we want to look at, compared to a ship shape where it's usually the longitudinal axis that we're heeling over on. And our third and final and sort of the new approach we're going to be talking about today is the idea of wind geometry, which is doing all the wind overturning moment calculations directly from the geometry defined in the hull. And so we'll look back at Ship Project Editor here with our semi-submersible. And all our geometry here will be defined in the spaces. So you see we have, first off, just our normal hull spaces here, the deck, the pontoons, and the columns that we'd consider contributing to the hydrostatics of the vessel. But then we have all these geometry objects in red with volume factors of 0. And these will be all of our topside geometry that will be important for the wind calculations. So here I'll go ahead and select this checkbox to show the windage columns. And you'll see we have a new set of columns in white here in the middle, which are all of our wind variables that we'll need to define for doing a direct geometry approach for wind calculations. And so starting here with the wind shape factor, this is typically a factor defined for different topside geometry types. So you can see we have different values here for, say, the deck versus the pontoons of 1. Something like the columns, which we'd expect to be a bit more cylindrical in shape rather than boxy, we have a shape factor of 0.5, showing that as the wind hits it, the cylinder isn't as blunt an object as, say, the rectangular prism of hitting this face. So they will have sort of less of a contribution to the wind force and in turn the overturning moment. And again, other values for, say, the crane or the crane arm. And these values typically come from criteria, and the default ones that we use here come from the 46 CFR here, where if we scroll down to the bottom here, you see we have a table of the different shape factors defined for, as I said, cylindrical objects, any hull surface or deck house surface. And you see here we have the underdeck areas with stipulations whether it's smooth or if there are other exposed objects underneath the deck. And what these do for the calculation is that they're essentially a multiplier on the wind force acting on each of these objects. And we can dive a bit more into the calculation later. The next factor, which is also a multiplier, is the idea of wind permeability. And the idea here is if we have, say, this crane arm where, let me zoom out a bit so we can see it. If we have, say, this crane arm, which may not necessarily be a solid rectangular prism as it's defined here, but made up of different trussing, as the wind hits it, there will be open spaces where the wind can pass through more easily, whereas if it hits the truss, then it's actually hitting the crane arm. And same idea for any other objects. If we have maybe a grating where it's not completely solid and wind is able to pass through, we can adjust this wind permeability multiplier to sort of reflect those differences. And it should be noted that this idea of permeability here for wind is different from the compartment permeability that you may be used to from, say, damage conditions or for different flooding scenarios. So this should be defined separately from those compartment permeabilities. And these aren't as necessarily strictly defined in the criteria, although one example from the CFR here is, again, where it's talking about open truss work, where the projected areas can be taken as some percentage less than the actual projected area of this rectangular prism. And so what we do is we take whatever value they say here in the rules and change the multiplier for, it would be like the crane arm. And that would reduce the wind force and in turn the wind overturning moment sort of effects from the crane arm. Third column we're looking at here is the idea of simplifying the wind model. And this is generally used for looking at speeding up certain calculations, and it draws a much simpler bounding box when doing the area projections when compared to, or rather than strictly turning the object and getting the exact sort of shape of the object when it's projected. And finally, we have this idea of excluding from shadowing, which is, say we have the wind coming from fore to aft here. And so this drill rig in the middle would be blocking some portion of the deck house behind it. And so if we were to not include shadowing, we would be including the effects of the wind hitting the drill rig in front, but also whatever portion was being blocked before. And we'll talk about this more when looking at the vessel and the wind analysis model, as there's a much better visual representation in there. So that's kind of our overview of the wind geometry definition in Ship Project Editor. Essentially taking any of these volumes that we have defined for the vessel, adding them to the hull, and then making sure these wind variables are defined properly for anything that we want to include for our wind evaluation. And again, this is a method that's better suited for offshore vessel wind analysis when compared to something like the ship profile, since we're now taking directly to geometry and doing the calculations out. So that's it for the ship project editor and sort of wind model definition side. And so next we'll move into looking at our wind analysis tool. And so what we'll do is we'll open up our existing semi-submersible model. We'll explain and set some of the important wind calculation settings. We'll actually run it and let it do its thing. We'll save out a model with the new results, which is a defined wind table for the vessel, and then take that vessel and the results and go into HECSTAB to do a very simplified intact max kg analysis, just to show what we can do with the results. I'll go ahead and we have our vessel opened up in the Herbert-ABS wind app. And just first looking at the UI, you can see that we've taken a lot of the more modern user interface approaches that we've done with HECSTAB version 9. We have the ribbon bar up here with sort of our more used settings. And so we can configure the different wind types, our headings, drafts, heels, and trims to generate our wind matrix. We have our run options and then some display options for units. Looking first in the top left, we have our global calculation settings for our wind analysis. And so you see here we have the wind type, which we select to choose the different wind speeds and those other options that we saw in Ship Project Editor. And then here we can actually set our wind speed to whatever else we like. We'll keep the default 51.44 meters per second. We have this air density sort of factor here, which is typically defined in the criteria. This one is coming again from that 46 CFR criteria we showed previously. Next, we have the pressure distribution types, where we have two options, either a constant or a gradient. A constant will apply the same sort of wind pressure and generate the same wind force, no matter where we're looking at on the vessel vertically. Whereas a gradient will take typically a reference height, some distance above the water line, and then do a decay from the reference point down to the water line. And so while we move down along the vessel, we'll have different wind pressures and let's have different forces applied in different sections of the vessel vertically. You can see here, if we choose the constant selection, we sort of lose some options compared to the gradient, which has these options for the different heights. First one we'll look at is the height coefficient options, where we have three different ones available. First, the wind exponent and reference height, which is sort of the method I described with a reference height and a decay through some exponent. For this option, we have different strip sizes available that you can define. And so this will determine how finely the vessel is broken up vertically to calculate the different wind pressures. The next two are basically the same. They are height coefficient lookup tables. And what this does is it breaks the vessel up into equal chunks along vertically and gives it another multiplier. And so we can go into the customization to look at how this is defined. Here we have the reference height above the water line. So this will be the lowest point of whatever section we're looking at. And we have a height coefficient that correlates to that. So any portion of the vessel that's between 0 and 15.3 meters above the water line will receive a height coefficient or multiplier of 1. Anything in between 15.3 and 30.5 meters will receive a height coefficient or multiplier of 1.1, and so on going along the table. And again, the default we're using here comes from the 46 CFR shown previously. This height table is customizable, so for any different criteria with, say, different ranges of heights or different wind or height factors or height coefficients presented, those values can be changed in the table. We'll go ahead and keep the height coefficient lookup table as our option here. Next calculation option that's important is our calculation for the center of lateral resistance. So just as we have area exposed above the water, which is acted upon by the wind, we also have areas of the vessel below the water, which sort of act as the counter to our wind force. And our lateral resistance option here determines how the center of this area below the water is calculated. First option, using projected area, essentially does a area moment calculation from the water line to determine where the center of underwater projected area is. The next option is the half draft option, which, as it states, simply places the center of lateral resistance half draft below the water line. The next one is the thruster center. So if there are any thrusters defined in the ship model, we're able to use the centers of those as the center of lateral resistance, say if we were using the thrusters to counteract the wind force instead of just relying on the underwater area. And then finally, we have the user-defined option to set it to whatever you'd like for either evaluation purposes, what have you. The next option, which is the data source option, determines what we use for generating the projected areas for the vessel. And really the important one we want to look at here is the 3D geometry. Of course, since we're looking at an offshore vessel and we want to evaluate it for multiple different wind heading angles. But there is also the 2D wind profile option if you're only interested in the beam winds, or if you're looking at something just ship shaped in the wind analysis tool. And the final option we'll talk about is this suppressed shadowing option. And here, compared to the one we saw in Ship Project Editor, this defines it globally for all the spaces available on the vessel instead of turning it on for individual spaces. We'll go ahead and turn that one on. All right, so moving on to the next panel here, we have our wind parameters, which is similar to the table we saw in Ship Project Editor, where we have all of our wind headings, heels, drafts, and trims defined. And we'll go ahead and define these out now. First is the wind headings, and we'll do this in 30-degree increments going all around the vessel. Next, for our drafts, we'll add just a couple more going from 10, 15, and 20. Our heel angles, we'll add a few more as well, going from 30 degrees to port to 30 degrees starboard. And for simplicity, we'll keep the trims we have defined here. And so the final panel we can look at before running our calculations is this spaces panel, which is similar to the one that comes from Ship Project Editor. You see we have, again, the names of all of our volumes. We have the shape factors here, which are editable in case the ones that we defined previously we want to change for any reason. Same thing available for the wind permeability. We can change them on the fly within the program without going back and editing the ship project itself. And finally, the exclude from shadowing options that we can turn on individually. And so with that, we'll go ahead and let the calculations run. So we'll set up all of these wind cases and new calculations for the wind overturning moments. And so now that's all run, and we can see in all of our results views, we have this green checkbox indicating that calculations are run and up to date with all of the settings that we have applied. First sort of important results field is first off the summary results, which gives the important values for each of the conditions that we were looking at. So for every draft, keel, trim, and wind heading that we have defined in our wind matrix, we get out the resulting displacement, the wind overturning moment, and the wind arm calculated from these two values. Next, we have the VCF, or vertical center of force. This is essentially the vertical center of all the above water area. We have the CLR, which is the center of area below water. And then the projected area is both above and below the water line. And so if we scroll through this, you see we have a really long list of all of our results that are available, going from 10 to 20 meters draft, and all the different angles we were looking at. And if I want to go into a specific condition and look at any of the individual components, we'll go ahead and look at the 90-degree heading at even keel and 20 meter draft. And we can go into detailed results here, and you'll see we have each piece of the vessel broken out here based on their individual contributions to the overturning moment. First off, up top, you can see we have sort of a summary one line of the condition we're looking at. We have the wind heading, the draft, heel, and trim. We have the vessel displacement in this condition, and the wind arm, which is usually the value we care about most. And so we can go in and expand any of these detail rows, and you see we have first off the deck with its contribution to the overturning moment, the wind force that was applied on the vessel. Looking in this view, the wind force that was applied to this projected area of the deck, the VCF of just the individual deck component. There's no CLR since it's completely above water, projected areas, and the various factors applied from the shape factor, height factor, and permeability. You can see we have these sort of color coded. So as you look around the 3D view of the vessel, you can kind of correlate them to the different pieces that, or you can correlate them to the different rows you see here in the table. Also, what we can look at is the 2D view here, which as we go around, we highlight the different components that you've actually selected, making just the visual a little bit easier. And these represent the actual projected areas that are used to run these calculations. So you can see we have each individual component highlighted, and they will each correlate, at least with the settings we have turned on, to the individual rows in this table. So now let's play around with a couple of these settings. First off, we can look at the height coefficient setting, and we can go and look at the wind exponent and reference height. So we'll start with the default strip size, about 50 meters there. Rerun just that calculation. And you can see now with this switch to the height coefficient, we have actually the different strips that the program is using to break the vessel up vertically to do this version of the height coefficient. And you can see in the polygons column, for something tall like the drill rig, we have it broken up into multiple, as it says here, 6 different polygons to get different height coefficient values for each section. And so if we do this a little bit finer, say for 1 meter, let it run and switch back. You can see now we've broken up very finely into these 1 meter strips. And we can go to the opposite extreme of, say, 100 meters, run this case, and we have essentially what we saw before with a singular polygon for each of these different components. So we'll switch back to the height coefficient lookup table. And the next setting that we'll look at is this idea of suppressing shadowing, which we'll turn off globally now. Let this run. Come back. And now you see in our summary table here for the detailed results, we have fewer columns available. And what the suppressed shadowing is doing is it's combining these different components that have the same shape factor into singular polygons to do the overturning moment calculation. And so you can see here for the deck, that was one that had just a unique shape factor. All these 5 components here all had a similar shape factor, so they were combined to be considered one polygon, and so on for these other ones. And so this will be easier to visualize in, say, one that does have shadowing. So this condition, you can see in the results here, says it needs to be updated since we did change this shadowing option, but we can still view the previous results. So with the option to suppress shadowing turned on, you can see that for the deck house where it's overlapping with both the pedestal, or with the pedestal, this part of the crane, and the drill rig, you see there's this transparency where we're showing both areas, which means that considering the contribution to the wind overturning moment in this section for both the deck house as well as the drill rig. And the same is true for this section here of transparency on the crane and the deck house, and here as well, though they look to be the same color, but their contributions are counted in this section area for both pieces. You can see it again in the 3D view. You can see we have this shaded portion being hit by the wind here on the deck house, as well as you can somewhat see it here behind for the drill rig. And the same is true for the pedestal behind the deck house and that portion of the crane. So now if we come out of this to the 2D view with shadowing turned off now, or with shadowing, and run this condition, you can see the effects of how those polygons are combined in here. And so we'll expand all of these. So first off, we can see that the pedestal disappeared since the pedestal and the deck house have similar shape factor. So they were combined into one area. So that's gone now. Here we see the transparency gone for the interaction between the crane and the deck house. And what we're doing here is we're taking the area with the higher shape factor and keeping that as true for this portion of the area. So the crane ended up with a shape factor of 1.5, which is higher compared to the deck house with just 1. And the same thing for the drill rig, where we had the shape factor of 1.25, which is higher, so we take its contribution compared to the deck house. Another thing we can see here is for these columns, we have 4 polygons and 4 corresponding spaces. And this comes from the fact that we're split at the water line at the columns here. So we have a polygon available for the underwater portion, which is calculated for the CLR, and then the polygon for the above water portion, which is calculated for the VCF. What we'll do now is we'll go back to the original settings we had, rerun all the calcs just to make sure we're fully up to date. And that is basically it for our wind analysis tool. What we can do from here is we can go up to File here, and we can actually save out this ship. And what it's going to do is update the wind table that we had shown previously as blank for this model with all of the results from our summary for all of these different vessel conditions. And so we'll save this vessel with a different name. Say it has our tables, save. And this pop-up shows here saying that we're going to be taking the wind results and overwriting any of the ones which are saved in the model, which we didn't have any saved in the model, so we'll say that's okay. And now we can open up that ship we just saved out. Close out of that. Say that's okay. Go to the one we just saved out with the table. You can see here we have a higher file size, which is all that wind table data that we saved out. And from the wind analysis tool, we have our wind table filled out. And so this is, again, a much faster way of entering the data into our wind table compared to doing it by hand or creating a spreadsheet of all those results and bringing them in through the macro. So now with our new model defined and saved, we can go ahead and open up HECSTAB. Minimize that for now. For later, go to where we saved our newly defined vessel and open it up. And you can see now if we go into our calculation options under wind, our hull table lookup data option is no longer seen as invalid since we now have the wind table defined from our Herbert-ABS wind app. So we're going to do like we said, we're going to go ahead and do an off-axis max kg run for the intact, just to do a simplified case. We'll keep all of these variables defined the same. We'll edit our heel angles just to get a bit wider range on the heels. We'll go ahead and use the wind table lookup data that we had just defined in the wind app for our run. Go in and use sample MODU criteria for column stabilized units as our GZ criteria. And finally do some range of drafts. Step it by 5 from 10 to, we'll just keep our 10 to 20 to keep this quick. So now we have all of the data we need to find for our intact max kg analysis. So we'll go ahead and run. Let it set up our conditions for us, the 3 drafts we're looking at. Let this run out. 1, 2, and 3. And essentially now what we've done is we've been able to do in here just a relatively simple wind analysis using the results from our wind analysis tool very quickly directly from the geometry that's defined in the vessel, rather than having to calculate out all of those wind overturning moments separately. You can see here for a wind model source, in the future, we hope to directly expose the calculations using the wind geometry model here in HECSTAB so that these runs can be done right in HECSTAB without the need for defining a wind table first and then coming back into the program here. So with that, that's been sort of a very quick and high-level overview of our new developments for wind modeling and analysis, both with our new tool, Herbert-ABS Wind, as well as in HECSTAB.
All right, thank you, Brandon. While you were giving your presentation, a couple questions came in through the webinar. The first one was questioning when healing the model is the lift component from horizontal surfaces like the deck box included in the overturning moment.
So it is included in the overall overturning moment, but the lift itself isn't directly calculated. How that's being handled is with these shape factor values. And so you can see here, for instance, with the under deck areas, we have this higher shape factor sort of to account for that. And these other shape factors do much of the same thing.
Excellent.
What we've seen in some other programs where they do directly calculate the lift, this shape factor isn't really exposed, since it would be double counting it, calculating the lift and using this multiplier.
Okay. And then the other question was, is the wind exponent value editable?
Not currently in the Herbert-ABS Wind app, although we do have it on the list to expose more of those values in the calculation settings.
Okay. Well, that was all the questions that we got. Brandon, I want to thank you for doing an excellent job on presenting this. And for those of you that are HECSTAB, HECSELV annual maintenance, you should be getting an email out shortly. This will be in our August release with everything being exposed and everything that Brandon has shown here. And as always, we welcome your feedback, comments, questions, suggestions, and recommendations. And we'll continue looking forward to working with everyone. Thank you very much and have a good day.